Good morning friends. Here in the previous session we have discussed integrals of complex valued functions of a real variable. In the next session we will study integrals of complex valued functions of a complex variable. We will see that integrals of complex valued functions of a complex variable are defined on curves in the complex plane rather than on just intervals of the real line. Classes of curves that are adequate for the study of such integrals are introduced in this session. First we have definition of a continuous arc. An arc C in the complex plane is a set of points z is equal to xy such that x is equal to x of t, y is equal to y of t, where a less than or equal to t less than or equal to b. Equation number 1. Where x of t and y of t are continuous functions of the real parameter t. The above definition establishes a continuous mapping of the interval a less than or equal to t less than or equal to b into the xy or the complex set plane, and the image points are ordered according to the increasing value of t. It is convenient to describe the points of C by means of the equation z is equal to z of t, where this t varies as a less than or equal to t less than or equal to b. Mark it as equation number 2. Where z of t, we can write z of t is equal to what? X of t plus I y of t. Equation number 3. The sense of increasing t is called the positive sense on C, and we say that C is oriented by 2. Next we have definition of simple arc or a Jordan arc. The arc C is a simple arc, or we can call as a Jordan arc if it does not cross itself. That is, C is simple if z of t1 not equal to z of t2 when t1 not equal to t2. Next we have a definition, that is, when the arc C is simple except for the fact that z of b is equal to z of a. We say that C is a simple closed curve or a Jordan curve. So, next we move on to example. The polygonal line, that is, we can say z is equal to x plus ix, here 0 less than or equal to x less than or equal to 1, that is x is in between 0 and 1, and the value of z is equal to x plus I whenever this x is in between 1 and 2, that is 1 less than or equal to x less than or equal to 2. Mark it as equation number 4, fourth equation. Consisting of a line segment from 0 to 1 plus I, that we can, here this is our x axis, y axis, or we can say real axis or the imaginary axis. Here we have the real values 1, 2, 3 etc. Here we have imaginary values 1i, 2i, like that. So, here the line segment is from 0 to 1 plus I. 1 plus I is here. This is our 0, this is our 1 plus I. 0 to 1 plus I, and followed by 1 from 1 plus I to 2 plus I. That is, here we have 2 plus I coordinate. This is our imaginary axis, here is our I, here is our 1 and 2. This is our 2 plus I coordinate, is an example of a simple arc. We can write here 1 plus I, here it is 2 plus I. This is an example of a simple arc. Next we have the unit circle. Next example is unit circle, that is z is equal to e raised to I theta. This we can write as what? Cos theta plus I sin theta. Here theta varies from, of course it is from 0 less than or equal to theta less than or equal to 2 pi. Equation number, next equation number is 5. About the origin, it is a simple closed curve oriented in the C clockwise direction. Sorry, it is in the anti-clockwise direction. That is, this is our curve C. It is in the anti-clockwise direction. Similarly, the circle, that is z is equal to, the one is z is equal to z naught plus e raised to r e raised to I theta. Here also theta varies from 0 and 2 pi. Mark it as next equation, that is equation number 6. Here it is centered at the point z naught. It is z is equal to z naught plus r e raised to I theta, that is z naught is the center, and radius, this is our radius r. R is also this is a simple closed curve oriented in the counterclockwise direction, that is, it is just like this. This is our center z naught, this is our radius r, it is in the direction counterclockwise direction. Next we have next is z is equal to e raised to minus I theta. Our z is e raised to minus I theta, 0 less than or equal to theta less than or equal to 2 pi. Next equation is number 7. It is not the same as the arc described by the equation number 5. That is, the set of points is the same, but now the circle is transversed in the clockwise direction. Here it is e raised to minus I theta. So, it is of the form center, of course 0 0, 1 I minus 1. It is in the clockwise direction. This curve is in the clockwise direction. Next, the points on the arc, that is z is equal to e raised to 2 I theta. Z is equal to e raised to 2 I theta. Here again theta varies from 0 less than or equal to theta less than or equal to 2 pi. Equation number 8. It are the same as those making up the arcs 5 and 7. But the arc here differs, however, from each of these arcs, since the circle is transversed twice in the counterclockwise direction. So, suppose that the derivatives x dash of t and y dash of t of the components of the function, our function is z of t is equal to x of t plus I y of t, used to describe an arc C exist and are continuous throughout the entire interval a less than or equal to t less than or equal to b. Under this condition, C is called a differentiable arc. Since the derivative of z of t, that is z dash of t is equal to x dash of t plus I y dash of t. Next equation number is 9. It follows that the real valued function, that is mod z dash of t, which we can write as square root of modulus of x dash of t square plus modulus of y dash of t square is integrable over the interval a less than or equal to t less than or equal to b, and then the length of the arc, it is given by L is equal to length, L is equal to integral a to b mod z dash of t dt. Equation number is 10. We note that expression 10 is the definition of arc length in calculus. Next we have invariance of this expression, last expression. The parametric representation used for an arc C is of course not unique, and the value of L given by this expression number 10 is invariant under certain changes in that representation, as one would expect. To be specific, suppose that t is equal to phi of tau. Here tau varies from alpha less than or equal to tau less than or equal to beta. Next equation number 11. Where this phi is a real valued function mapping the interval alpha less than or equal to tau less than or equal to beta onto the interval a less than or equal to t less than or equal to b. That is, actually our figure is like that, like this. Here we have alpha, here we have beta, t varies from a less than or equal to b. It is just like this. We assume that phi is continuous with a continuous derivative. We also assume that phi dash of tau greater than 0 for each tau. This ensures that t increases with the tau. With the change of variable indicated in the equation 11, expression 10 for the length of C takes the form L is equal to, it is integral alpha to beta mod z dash of, we have phi of tau into phi dash of tau d tau. So, if C has a representation that is z is equal to z of tau, that we can write z is equal to, this is z and this is our tau, z of tau is equal to z into phi of tau. Where this tau varies as alpha less than or equal to tau less than or equal to beta. Next equation number is 12. The fact that we have z dash of tau is equal to, here we have z of tau is equal to z of phi of tau, and we have z dash of tau is equal to z dash of, the next is phi of tau into phi dash of tau. Equation number 30 enables us to write expression 10 as, what we can change our equation number 10 as like this, that is L is equal to integral alpha to beta, we can write it as, it is from a to b, that is L is equal to integral from a to b mod z dash of tau dt. equation number 40. Thus, the same length of C would be obtained if representative 12 were to be used. Next, we have unit tangent vector. If the equation, that is z is equal to z of t, of course t varies in between a and b, represent a differentiable arc and z dash of t not equal to 0 anywhere in the interval a less than t less than b, then the unit tangent vector, that is unit tangent vector is t is equal to z dash of t by mod z dash of t. Next equation number is 15. This is our vector t. This is actually vector t. It is z dash of t by mod z dash of t. It is well defined for all t in that open interval with angle of inclination argument of z dash of t. Also, when this vector t turns, it does so continuously as the parameter t varies over the interval a less than t less than b, that is t is in the open interval a b. This expression for t is the one learned in calculus when z of t is interpreted as a radius vector. Such an arc is said to be smooth. Actually, the definition is that if the arc given by the function z of t has continuous derivative z dash of t which does not vanish for any value of t, the arc has a continuously turning tangent and then the arc is said to be smooth. This is actually the definition of smooth. In referring to a smooth arc, that is z is equal to z of t, where t varies in between, t is in the closed interval a b, then we agree that the derivative z dash of t is continuous on the closed interval a b, that is a less than or equal to t less than or equal to b, and non-zero on the open interval a b. Next, we have move on to the definition of a contour or piecewise smooth arc. A contour or piecewise smooth arc is an arc consisting of a finite number of smooth arcs joined end to end. That is, a contour is simply a continuous chain of finite number of smooth arcs. Hence, if equation, that is z is equal to z of t, a less than or equal to t less than or equal to b, represents a contour, z of t is continuous, whereas its derivative, that is z dash of t, is piecewise continuous. Next, we do some examples. So, recalling the example 1, that the polygonal line that we have discussed, z is equal to what, z plus ix when 0 less than or equal to x less than or equal to y less than or equal to 1, that is z of x is equal to, we have discussed polygonal line, that first one is x plus ix. Here x varies in between 0 and 1, 0 less than or equal to x less than or equal to 1. Here it is x plus I, where 1 less than or equal to x less than or equal to 2. This is the one we have discussed in the example 1, polygonal line. This consisting of a line segment from 0 to 1 plus I followed by one from 1 plus I to 2 plus I is an example of a simple arc. This polygonal path is a contour also. Why? Since we have z dash of x, z dash of x is equal to 1 plus I, of course 0 less than or equal to x less than or equal to 1, and the other one is 1, that is here we have only x term 1, where this Here we have the value 1 less than or equal to x less than or equal to 2. It is a piecewise continuous function. Next we have simple closed contour. When only the initial and final values of z of t are the same, a contour C is called a simple closed contour. The next example is, that is the unit circle. We have discussed z is equal to e raised to I theta, where of course this theta varies in between 0 and 2 pi. This is our equation number 16. About the origin is a simple closed contour oriented in the counterclockwise direction. Since we have z of theta is equal to e raised to I theta, and what about z dash of theta? It is I e raised to I theta are continuous, and z of 0 is equal to 1, which is again equal to z of 2 pi. Similarly, the circle, that is z is equal to z naught plus r e raised to I theta, that is 0 less than or equal to theta less than or equal to 2 pi, equation number 17. It is centered at the point z naught and with radius r. It is again a simple closed contour. Next we have the boundary of a triangle or a rectangle taken in a specific direction is also a simple and closed contour. Next we have a simple definition. The length of a contour or a simple closed contour, it is the sum of the lengths of smooth arcs that make up the contour. We have some discussion about domains and boundary associated with a simple closed contour. Associated to any simple closed curve or simple closed contour C, there are two distinct domains, one of which is the interior of C and is bounded. That is, this is our interior of C and it is bounded. The other, which is the exterior of C, this is the exterior, and of course it is unbounded. The points on any simple closed curve or simple closed contour C are bounded points of these two domains. Next we have an important theorem, and it is very tough also, that is Jordan curve theorem. The theorem says that is, if J is a Jordan curve, that is, it is simple closed curve, and if X is a point in the interior of J, this is our J, that is our Jordan curve, and we are taking a point X in the, this is our interior of J and this is the exterior of J, and here we are taking a point X in the interior of J, and Y is a point in the exterior of J. Here I am taking the point Y, here it is our X. Then any straight line or a curve joining X and Y must meet J at some point. It is, of course, we are going to join these 2 points, that line must cut the curve. Jordan curve theorem is intuitively obvious but very difficult to prove. So, hope you enjoyed the session. See you next time. Till then, take care.